Hello, is the sound on? Is it on now? Ooh.
Hallo Frederik, skal ikke hjem og spise? Nu skal vi lige have den her forberedelse. Okay, så op til sidste en. Nej, jeg har simpelthen spist. Har den hjem latterligt mange.
Hello. No sound? Ah.
Ej, hello. This is too much. Yes, that is too much.
Well, I don't know how to fix that. Let me try.
Torsdag eller sådan noget. Det var hyggeligt. Ej, okay, vent lidt. Min søster kommer. Jeg kan spørge mig.
Is there any sound now? No sound. Mm. I don't know how to fix it, but I'll try to talk loud, and hopefully it will be captured by my PC, but who knows. So what I'm going to do today is that I'm going to talk about integration techniques, and it's kind of nerded because do you really have to be able to do the integration by hand, or can you just use Maple? Well, I'll show you a couple of techniques that you can use, and then you can understand how this works, and maybe you have some background when you use Maple, so you can check what you are doing. But the question, or the thing I'm going to talk about today is how do we find indefinite integrals? I'm going to talk about partial integration, and the method of substitution, And then I'm going to end up by giving an example with a curved integral. And I'm going to end up by actually determining the curve length of this. So, let me start. Partial integration. I'll give you the formula for partial integration. You have the integral of a product of functions, and this is the indefinite integral. And this is equal to this formula here. I just return to the different terms in this. But if you have a product of two functions, you should look for a product. Then it is equal to the indefinite integral of the first factor here times the second factor, and then minus the integral of this indefinite integral of the first factor times the derivative of the second factor. And you can easily prove this by just differentiating this formula. We're just going to use it. So when you're looking for a way to use this formula here, you should look for a product in your integral. And if you look at the right-hand side, then you're looking for a factor of your integral that is easy to integrate. It's easy to find an indefinite integral of that function. And also, you see, you're not finished when you have used this formula, because you still have an integral you have to solve. So the thing is that this integral should be easier to compute than the original one, else you are not getting anywhere. So let me start by giving you an example of using this. I'm going to integrate the exponential function times x. And here you have the product of two functions. This is very easy to integrate because the indefinite integral of this function here is the function itself. And when you differentiate this one, you get a 1. So there's hope for simplification here. So what I'm going to do is that I'm going to put f of x equal to this exponential function. And then I have my indefinite integral that is equal to the exponential function. I have this one, and then I have the derivative of this one is equal to 1. Okay, so let's try to use this one. So instead of this one, I should put e of x, and then g of x, which is x, and then minus the integral, and I still have this f of x, which is e of x, and then the derivative of the g function, which is a 1. Now this is just the integral, the indefinite integral of the exponential functions. So this is the exponential function itself. So I get ex times x, that was the first term here, and then this integral is e of x. And then you just write some constant, here.
Wouldn't it be minus?
You do that. Well, I better spell it. Sorry?
Wouldn't it be a minus? A constant?
A constant?
You are subtracting all the integrals, so shouldn't it be a minus, the constant? Or is-
No, it doesn't matter because it's an arbitrary real number, so you can just put it here. And this is well, you should do this because then you make the signal that this is determined apart from this constant, this indefinite interval. Whenever you have to compute a definite interval from this, then this constant doesn't matter. It goes out of the equation, so to speak. So let me take another example. I have here the indefinite integral of the product of these two functions. Again, I have x. So, and you get a 1 when you differentiate this. So you should probably use this as your g function. And cosine hyperbolic of x is very easy to differentiate and integrate. So let me repeat this. You have that derivative of cosine hyperbolic of x is sine hyperbolic of x, and also sine hyperbolic of x is, no, not prime here. It's simply the sine hyperbolic of x, and then cosine hyperbolic of x. I'm going to use the hyperbolic functions later on in order to find an integral, so I need the fundamental relation later on, so I'll just cite it here. So remember, when it's a trigonometric function, that is cosine and sine, you have a plus sign here, but for hyperbolic cosine and sine, you have a minus sign. Now, so I should put f of x, because this is the easy one to integrate, equal to cosine hyperbolic of x. Then I get the indefinite integral of this one. You see here, if I integrate this one, I get sine hyperbolic of x, because if I differentiate this, I get cosine. And then, of course, I put g of x equal to x, and this means that I have the derivative here. And now I can simply, from the general formula up here, I can write down the solution. I get the indefinite integral of here, so I write sine, and then I have my g of x, and then minus the integral of this function here, and then times g prime, that is the derivative of the g function, and this is a 1. I just put the x in front, because that's more pretty. Here I get the sine, so I should find an indefinite integral of this, and from what I have shown you, this is cosine x, and then you add some constant, arbitrary constant. So this is the result. One final example on partial integration. I want to compute this this way. Here again, I have the product of two functions. One is x squared, and the other one is ln x.
Sorry.
This is ln x. So which one to choose? Which one is the easy one to integrate, and which one is the easy one, or which one gets simpler when you differentiate it? And for one thing, you don't know the indefinite integral of that. Or maybe you do, but so you should probably choose this as g of x. And moreover, when you differentiate ln x here, you get 1 divided by x. So this is in a sense simpler. And of course you can integrate this one. So what I do is that I put f of x equal to x squared, and this means that my indefinite integral is 1/3 x cubed, like this. And then I put g of x equal to ln of x, and then I get that g prime is equal to 1 divided by x. Again, you have to assume you are in certain x intervals, because this is only valid, well, you are in the domain of the function, so, and this is only valid when x is positive. So you're away from 0. So let's just use the formula again. You have to put in capital F here. That will be 1/3 x cubed. And then the g of x, that is ln x, and then you should subtract this interval here. You still have 1/3 x cubed. But now you have the derivative of g, and that is 1x, like this. X cubed divided by x is x squared, and we have just computed the indefinite integral of this one, that is 1/3 x cubed. So you have 1/3 times 1/3, that is 1/9, x cubed, and then again plus some constant.
Sorry.
Yeah.
The integral of the sign is minus cosine, right?
The minus sign where?
In the other exercise, in the previous one. The integral of the sign is minus cosine.
It's minus, it comes from here.
The integral of the sign here should be plus cosine, the answer.
Yeah, but you should remember these relations. This means that the indefinite integral of sine is equal to cosine, and similar to here, the indefinite integral of cosine dx is equal to sine. They do not change sign. That's the reason. Okay. This was the easy part. Now I'm going to talk about substitution, which is a little bit more difficult. And again, I will start out by giving you the general formula. Here you have a function, a composite function. So you have an inner function g and an outer function f, and then it's multiplied by the derivative of the inner function. And this is equal to this integral and where t is equal to this inner function. And it can be hard sometimes to find out what g and f should be, but let's do a couple of examples, and hopefully you will get the feeling for it. What I want to do now is I'm going to integrate x times sine, and this is the trigonometric sine here, sine function. I want to compute this indefinite integral. Well, first of all, you should look for a composite function, and you have a composite function here. The inner function is x squared, and the outer function is the sine function. So let's see if this actually works. So I put t equal to g of x, which is then x squared. So this is the inner function. And then I get the derivative of this is 2x. Now the outer function would be sine of where t, of course, is equal to g of x. So if I put in t here, I should write x squared, and then I should multiply the whole thing with this one in order to get this one. But you see here, I have a 2 here. So when I multiply, I get a 2. But I could choose this as the outer function. Because when you then multiply the 2 together, you have the 1/2 here, you have the 2 here, and they cancel. So let me just write out the integrand, that is f of g of x times g prime of x. This one here is 1/2 sine of t, which is x squared. And then g prime is 2x, and you end up by having x times sine x squared. So this is in fact what you should integrate. So the first thing you should do is that you should integrate this one here is equal to the integral of f of t times dt, according to the formula. So f of t was 1/2 sine of t, and we have dt. So this is the result, or the integral. intermediate result, because this one here you can easily integrate. I get minus 1/2 cosine t, because the derivative of this one is equal to, or the derivative of cosine is minus sine of t, and then you get this integral here. And then you have some arbitrary constant. But you're not through yet, because you want to present the result in terms of the x variable. So you have to make the back substitution that you put t equal to x squared, and you get minus 1/2 cosine x squared plus this constant. So this is the result. Another example here. I have this integral 4x 1 plus 2x squared well, in this example is, well, in my mind, it's fairly obvious that the inner function is what you have in this parenthesis, and the outer function is this cubic function. So let's try to see if that will work out for us. So I put t equal to g of x, and this is equal to 1 plus 2 x squared. And then I need the derivative, and this is 4x. And this is nice because these 4x you find here. So, and then we have our f of t is t cubed. So let's check. It's always a good thing to check things out. You see here, we compute f of g of x times g prime of x. And this is, we put in, instead of t here, you put 1 plus 2x squared cubed, and then you should multiply by this one, you should multiply by 4x. So it works. It is in fact this integrand here. So I could say that this is equal to the integral of f of t according to the general formula, and then it's fairly easy to see that this is equal. When you integrate this, you have to add 1 to the exponent and then divide by this exponent. You get 1, 4 to the 4th plus some arbitrary constant. And again, you're not through until you have put in the value for t. So you should present the result in terms of x. 1 plus 2x squared. 4th plus a constant. This is the result. And the final example now is this one. and this is a broken rational function. You have polynomials in the denominator and the denominator. And often you do that you split the integral. This is one of the computational rules for integrals. That is, you take this as the first integral, and then this one as the second integral. And in this case, it's a good thing to do because this one you know by heart, because you learned that this Wednesday. So what is the indefinite integral of that one?
Arctan.
It's arctan. Yeah, that's good. So I need to, I keep right here, this is arcus and x. I don't have time to prove this to you, but maybe we can do it this afternoon if you want to. Now, the other one here, sometimes it's difficult to see what is this composite function. But you see, you have this 1 divided by x squared plus 1. So if you choose the outer function as 1 divided by t, and then this as the inner function, that is a possibility. So let's see if we can do that. So I put t equal to g of x, which is x squared plus 1. That is this one here. And then I get g prime of x is equal to 2x. Now then the outer function would be you see here I have a 2 here, but I have a 4 here, so I would choose 2 divided by t. Because then when I make the check, that is, I write down this integral, I get 2 divided by 1 plus x squared, and then times this derivative, which is 2x, and this is 4x divided by 1 plus x squared. And this is, in fact, the one that I'm looking for. So now it's easy to write down the solution. You have 4x divided by x squared plus 1 dx. And then this is equal to 2 times, I should just write down 2 divided by t dt. And you can integrate this. This is 2 ln t, the numerical value of that, plus some constant. But again, you're not through until you have made the back substitution. You have to put in t, which is x squared plus 1. But x squared plus 1 is a positive quantity. So you do not need these numerical signs, and you get 1 plus x squared plus this constant. So when I should sum up this integral here, I get 2 ln, or 2 the natural logarithm to 1 plus x squared, and then plus arctan to x plus some. Yeah. Let's take a small break while I clear the black box.